In Part 4 of Lecture 7, we will discuss deadlock detection. Some systems don't avoid or prevent deadlock. What they do is detect it and recover from it. That means that such systems need an algorithm for each of these two tasks. In the case of single instance resources, we can use a graphical approach. Let's take another look at our resource allocation graph. What we will do is simplify this by redrawing the request edges that currently run from process to resource. Instead, let's have them point directly to the process holding the requested resource. This is what the graph looks like after the redrawing of the request edges. Now we know at a single glance that P4 is waiting for a resource that P1 is holding. Which resource is not important? Similarly, P1 is waiting for a resource that P2 is holding, and P2 is waiting for a resource that P4 is holding. It is fairly straightforward to write a program that can detect whether there is a circuit like this in such a graph. This is similar to the banker's algorithm that we looked at before. We assume that certain resources have been allocated and that others have been requested. We'll look to see if there are any requests that we can fulfill. If that's the case, these processes can run through completion, and then their resources can be reallocated to other processes. We continue this until there are no more cases like this. If we haven't finished all our processes, there is a deadlock which includes this process. Let's look at an example. In this system, we have no remaining resources, but there are processes with outstanding requests. Since P2 doesn't need anything else, it can run through completion, and we can reassign its resources. We now have 3 A's and 3 C's available. But since P0 doesn't even need this, we can run through completion and we can reassign its resources. We now have 3 A's, 1 B, and 3 C's. This is more than enough to meet P3's request, and it can run through completion. We can then reallocate its resources. We now have 5 A's, 2 B's, and 4 C's. This is more than enough to meet P1's request, and it can run through completion. We can now reallocate its resources. We now have 7 A's, 2 B's, and 4 C's. This is more than enough to meet P3's request, and it can run through completion. We can now reallocate its resources. This is clearly not a deadlock, because there is a sequence of processes that can be completed. That sequence is P0, P2, P3, P1, P4. Let's look at this system with one change. Let P2 request a single instance of resource C. Since the only process that can run to completion is P0, let's assume that it does, and that we can reallocate its resources. We now have available a single instance of B. No A's, no C's. This is not enough to meet the demands of any of the other processes. Therefore, there is a deadlock between P1, P2, P3, and P4. Detecting a deadlock is important, but it is even more important that we recover from it. We have two options for breaking a deadlock. we can terminate one or more of the processes in the deadlock, or we can take back enough resources that one of the deadlocked processes can proceed to completion. Terminating a process is not something that we really wish to do, but it's better to terminate a process than to leave several processes unfinished in a deadlock. Here, too, we have some alternatives. We can terminate all the processes in the deadlock, or just enough to break the deadlock. Obviously, terminating them all seems fair on one level, but at the same time, it seems like overkill. We would prefer to kill only a few. Here, what determines the processes that are terminated and the ones allowed to run is whatever constitutes the lowest cost. Such factors include process priority, how far the process has progressed and how far from completion it is, the resources that it has used, the resources that it needs, how many processes need to be terminated, is it batch or is it interactive? Preemption would seem to be preferable because it allows the deadlocked processes to eventually run to completion. This also has a few issues that must be resolved. Which resource or resources do we preempt from which process or processes? When we restore the process that has had its resources preempted, where do we pick up execution? In other words, how far do we roll back? How do we make sure that the process doesn't starve? We have to make sure that it can eventually reclaim the necessary resources. Some researchers feel that none of these three approaches work best on their own, that we really need an approach that combines elements of prevention, avoidance, and detection recovery. One possibility is to divide our resource into a set of classes, in which each class of resources is subject to resource ordering. This should allow us to avoid deadlock and minimize its impact.